National 5, welcome to Storytime with Mr. Bull and with Nova. And today's book is all about quarks. So if you're thinking of taking higher physics, then this book is going to give you a little taste of what the course will be like. So let's dive in. This is called Quarks by Ruth Spiro. So it says, baby likes to build a tower with blocks. Okay. Baby builds with blocks, but nature builds with quarks. And you can see all the wee quarks jumping up and down there. Quarks like to stick together. 3 quarks make a proton or a neutron. And you can see lots of different quarks holding hands here to make protons and neutrons. Protons and neutrons stick together to make a nucleus. So if you bunch them all together, you make a nucleus. Okay? So that's all the wee quarks in there. Add electrons and that makes an atom. And you've got things like nitrogen, oxygen and whoosh there as well. Add atoms together and that makes a molecule. Okay, so things like methane and water. So if you're doing chemistry, then this might be helping you in your National 5 chemistry. Everything in the world is made of atoms and molecules. Even baby. And baby's just there. The baby's made out of molecules and atoms too. Scientists can smash a nucleus to break it apart. Smash. Baby thinks that sounds like fun, smashing things together. Smash, and our building blocks are all gone. Bye-bye tower. There we go. Well, isn't that an excellent book, National 5, about quarks? I think you could now sit part of the higher exam with ease. But what we're going to do for now is we're going to continue our Dynamics Part 2 revision. And I'm going to go through the PowerPoint, not in book form, but in PowerPoint form. So I hope this is going to be good for you guys in 3, 2, 1, and go. Well guys, you've seen many things during this lockdown. Another one there to remember, story time with Mr. Bull. But anyway, let's actually move on to more pressing issues. And that is our prelim revision for dynamics. Okay, so this week we're going to be doing dynamics revision part 2. So the things we're going to be looking at today are acceleration, velocity time graphs, and looking a little bit about W equals mg. Okay, so let's first of all look at acceleration. So you should know the equation for acceleration. It's a equals v minus u over t. So what do each of these little letters mean? Well, a is acceleration, meters per second squared. V is final velocity, measured in meters per second. U is initial velocity, so whatever it starts at in meters per second. And t is the time in seconds, okay? Now, you will have to memorize a few different ways in which to rearrange this equation. So a equals v minus u over t is standard, that's in your equation sheet. You will probably have to memorize the one that we always use in projectiles, which is v equals u plus at. But we'll talk about that when we get to projectiles. But that there is an important variation of this equation that you will also need to know. If you've got an equation sheet, I will be writing those down and memorizing them. So, just a wee quick point there at the bottom. If you are getting a negative answer, that is okay. Sometimes I think people get scared with negative answers. That's absolutely fine. That just means that the object is decelerating. Okay, so if it's negative, it's decelerating. That means that the initial velocity will be greater than the final velocity. I.e., if something's going from 20 meters per second down to 10, then it's obviously decelerating. It's getting slower. So let's look at 3 examples. The best thing to do with the acceleration is just do 3 examples. So example 1 says a car starts from rest and reaches a velocity of 8 meters per second in 4 seconds. What is the acceleration? So we'll go back and forth. So for this one here, we just took a equals v minus u over t. The final speed was 8. The initial speed was at rest, which means it's 0, and the time was 4. So that would give us 2 meters per second squared. Okay, so remember the acceleration units is meters per second squared. So that would be the answer for 1. Number 2, a trolley slows down uniformly from 8 meters per second to 2 meters per second in 2 seconds. So it's going down, it's going, we know that it's decelerating because it's slowing down. Calculate the deceleration. Okay, so again, you could actually just pause these videos and try them all if you wanted now, or you can just see what I'm about to do in a second. Okay, so for this one here, same idea, A equals V minus U over T. However, the final speed is less than the initial speed, so it's going to be 2 minus 8 divided by the time, which is seconds, 2 seconds, which would give you 2 minus 8 is minus 6. Minus 6 divided by 2 is minus 3 meters per second squared. So even though it's a negative, it just means that it's decelerating. Right, example 3 says a vehicle has an acceleration of 3 meters per second squared. What is the initial velocity if after 6 seconds it is travelling at 50 meters per second? Okay, so a different one here and a difficult one. So what I've started with is I've done V minus U over AT equals AT. How have I done that? Well, I've just brought the T up to times it by A, so AT equals V minus U. Let's just work it out from here. So I know the final speed is 50, so 50 minus U equals 3, because that's the acceleration, times 6, that's the number of seconds. So 3 times 6 is 18. We've got 50 minus U. If I rearrange that using my algebra, which shouldn't be difficult for you guys, U equals 50 minus 18, which should give us 32 meters per second. Okay, so just take it step by step. Don't overcomplicate it. Put the numbers in, try and get some values, and then rearrange at the end. Okay, so that is the 3 examples for acceleration. That should be hopefully very straightforward. Now, something that comes up again and again and again is the experimental procedure for acceleration. So that will often appear as 2 light gates with a trolley with a length of card, a stopwatch, a ramp, and some sort of QED computer. Now, what we need to do first is measure the length of the card. The length of the card is a really extremely important thing because that's going to give us the speed of the trolley at light gate 1 and at light gate 2. Using something similar that we talked about last week in instantaneous speed, we just find out the length of the card divided by the time it takes to cut the light gate. So we're basically going to be finding 2 instantaneous speeds, one at the light gate at the top and one at the light gate at the bottom. Okay? So if I go down to here, we're recording the time taken to pass through each light gate, and then, well, you would repeat the experiment further 5 times to get a more reliable result. But how would I find it out? Well, to find out A, you would calculate the initial velocity, which would be at the top of the ramp, because that's the start. And that would be the length of card divided by the T light gate 1. And it's moved across there because of the format issues, which is annoying, but you can get the idea. So that's U. V, which is the final velocity, is the length of card divided by the time of light gate 2. So can you see that we're then finding the instantaneous speed for the second light gate, which is at the bottom of the ramp. And then calculating at the acceleration, we just do that V that we found out minus the U that we found out divided by the time it took between the light gates, which is what the stopwatch was for. Okay, so to find the acceleration, V minus U over T. We found out V from the final light gate at the bottom of the ramp. We found out U from the initial light gate at the top of the ramp. And we've divided it by the time between the light gates. Okay? So, that's acceleration. Please remember that acceleration experiment because you will most likely be asked something along the lines of that. It always comes up in prelims and exams. So number 2 is velocity time graphs. A natural progression from acceleration says for any moving object it is possible to show how its velocity changes with time by graphing the velocity against time for the journey. So oftentimes in questions you will have to basically describe the motion that is being shown on the graph. So for example, on the left here, when it has a speed that's constant, we call that constant speed. Now ignore the letters here, I don't know what's happened, the formatting issue is gone again. It's always frustrating when it goes from Microsoft to Google Drive, so I'm just going to explain it, so listen to my voice, not what's on the screen. So the first one on the left graph is a constant speed. The one in the middle is constant acceleration because clearly it's accelerating, it's getting faster. And for the last one, it's constant deceleration because clearly the speed is getting slower. So a constant acceleration on the left, constant acceleration in the middle, and constant deceleration. If you can know those, that could be 1 mark in your exam, an easy mark. So, 2 things that we can do from velocity time graphs. We can calculate the acceleration using A equals V minus U over T. Okay, again, that T's moved over, I don't know why. A equals V minus U over T. Alright? So that is what we can use. For example, if I go back up here in the middle graph there, I could use the final velocity at the top of that gradient line minus the initial one, which is at the very start, and then divide that by the time it took to get from the starting point to the finish point. So I can actually find the acceleration of using the graph. Okay? And the acceleration is actually equal to the gradient of the line. Now you probably won't need to use that at all, but that is what the acceleration is equal to. A second thing is that the distance travelled is equal to the area under the velocity time graph. Now we should know this, National 5. The SCs are going through this right now, but you should know this. It is never distance, speed and time. It is never distance, speed and time. To find out the distance, it's always the area under the graph as soon as you see a graph, okay, with velocity and time on the axes. Always, always, always. So let's do an example. The graph below shows how the velocity of a car varies with time. So very similar to that middle graph that we saw. It's going from 8 meters per second all the way up to 32 meters per second after 4 seconds. So first of all, it says calculate the acceleration. So how are we going to calculate the acceleration? Well, to calculate acceleration, we're just going to do a equals v minus u over t. We know that the top final speed was 32, the initial speed is 8, and the time it took to do that is 4 seconds. So 32 minus 8 divided by 4 gives us 24 divided by 8, gives us 3 meters per second squared. That is our acceleration. Okay? So that's as we found out that from the graph. There's going to be plenty of examples like that, but the graphs will be extremely harder with actual grid lines. What is the distance travelled though? Well, the distance travelled, so when I look at this graph, the area under this graph could be split into a triangle and a rectangle. So a triangle and a rectangle. So when I'm doing this, I do d equals a dot u dot g. So remember, area under graph, it's always this. It's never distance, speed, time when you have a velocity time graph. The first one is a triangle, half base times height, plus the square, the rectangle at the bottom, which is base times height. So a half of 24 times 4. Why is it 24? Well, look at this triangle here. It goes from 8 to 32, so there's a height of 24 there, and I've still got a time of 4. So actually half of 24 times 4 plus, when I look back up again, I've got a rectangle. If I was to do a rectangle underneath that line, there'd be 8 times 4. So if I do that, 48 plus 32 gives me 80 meters. That is the distance, okay? So just find what all the area is under the graph. If I was to draw a line from the end point all the way down to the x-axis, how am I going to find the area of everything underneath that line? Okay? The next question says, calculate the car's average velocity. Well, we've just found the distance. We know the time on the graph, so it's just going to be 80, that's the distance, divided by 4, which is the total time, gives us 20 meters per second. Okay? So that there is how you would work that. That is a typical question that you could be asked. Now remember, sometimes you get these questions about the distance or the velocity when you get a graph like this in a multiple choice. So you're going to have to actually do a little small calculation in your head about the area under the graph before you proceed. So be careful, those are very tricky questions. Right, so what do we need to know? Calculate the acceleration using a equals v minus u over t. We know that the distance travelled is equal to the area under the graph, and when we describe part of the graph, we use phrases like constant speed, constant acceleration, and so on. So please, please, please know those 3 things for velocity time graphs. Now, let's move on to w equals mg. And very easy, mass is obviously the quantity of matter forming an object and measured in kilograms. It remains constant. So remember, we talked that, and even in S2, mass is constant. It does not change, it stays the same. Okay? If I was in the moon, or even if I was kind of falling in space somewhere, it's always going to be the same. My mass is what makes me. Okay, it's the quantity of matter forming an object. However, the weight is a force caused by gravity. So obviously, if there's different gravitational pulls, the weight will be different. So the weight of an object will change when different gravitational fields, and that is measured in newtons, whereas mass is measured in kilograms. So, some important things to note, okay? We have a capital W for weight, small m for mass, and we use G for gravitational field strength measured in newtons per kilogram. So that's where we get this equation W equals mg. And that's why we get newtons per kilogram, because if I was to rearrange for g, it would be W over m, which is newtons over kilograms. So on Earth, we should know, and this is very important, that the gravitational field strength of Earth is 9.8 newtons per kilogram. That is very, very important that you know that. 9.8 newtons per kilogram, we use it all the time in questions to come. Okay? And if there's ever a question that asks you about another planet, you have a data sheet with all the gravitational field strengths of all the planets on there. So look at that. So let's look at an example. An astronaut with a mass of 90 kilograms on Earth goes to Jupiter, where G is 23 newtons per kilogram. What is the astronaut's weight on Earth? Well, very quickly, weight on Earth is just going to be W equals mg, 90 times 9.8. Doing that in the calculator, I get 882 newtons. That is a standard 3 marks I expect everyone in National 5 to achieve. Okay? What is the mass on Jupiter? Well, we just said mass doesn't change, so the mass on Jupiter is just 90 kilograms. Very straightforward. Again, another question I did not expect people to get wrong. What is the weight on Jupiter? Well, we just do W equals mg again. 90 times 23 this time, not 9.8. It's 2,070 newtons. That, National 5, is simple, it's straightforward. Must be. Okay, so weight and mass. W equals mg. Weight is measured in newtons, mass is measured in kilograms, gravitational field strength is newtons per kilogram. Okay? Weight is a force caused by gravity. So remember, the gravitational field strength will cause a different weight on different planets. Alright? Now, that is everything for today. So that's just on acceleration, velocity time graphs, and finishing off with W equals mg. Next week, we're going to be moving on to talk about forces, Newton's first law, second law, and third law, which has a lot of questions. But National 5, yet again, excellent work. Hope this week's work is good, and I hope you enjoyed that little story time with Mr. Bullanova. Guys, have a great day and have a great week. Well done for listening.